Since we started Chapter 16, look at acids and bases, we've been focusing on monoprotic acids, acids that have one proton, and we called them HA. And we dealt with monoprotic bases, bases that picked up one proton in order to become protonated to get the conjugate acid of that weak base. So now we're going to talk about how does it affect the pH when we have a polyprotic acid, something that has more than one proton it can give up. Well, the awesome part is more than one proton means more than one equilibrium going on in your beaker at the same time. I can tell by your faces how happy you are to hear that. So let's look at some polyprotic acids. Poly means many, protic means proton, many proton acids. Most of them are diprotic acids. They have two protons. We have phosphoric acid, which is a triprotic acid, but there's not very many triprotic acids. So sulfuric acid we'll look at first because it's sort of an interesting anomaly. Sulfuric acid is a strong acid. So sulfuric acid, H2SO4, breaks apart completely to give us a proton plus a hydrogen sulfate ion. It's only the first ionization that is a strong ionization. So if we have a beaker full of sulfuric acid, we know the hydrogen concentration from the first ionization. Now, this hydrogen sulfate ion is the conjugate base of a strong acid. It's not interested in acting like a base. However, because it's a hemiacid or a half acid, it can do the acid thing. And this is a weak acid, so in equilibrium, it produces hydrogen ions plus sulfate ions. Now, because we think of these ionizations taking place in steps, losing one proton at a time, we can think about this one. Most of the hydrogen ion in solution comes from this first ionization. And what we're going to see later on is that the second ionization is really insignificant. So we can often treat them just like we treat monoprotic acids. Okay, let's look at carbonic acid. Carbonic acid is diprotic. We get a hydrogen ion plus a hydrogen carbonate ion. Then our hydrogen carbonate ion can do the same thing, and it can give up a proton to give us another proton plus the carbonate ion. Now, the phosphoric acid is our triprotic acid, and it also loses its protons one step at a time. So H3PO4, phosphoric acid, is in equilibrium with a hydrogen ion and a dihydrogen phosphate ion, which has a -1 charge. That ion is in itself a diprotic acid, so it can lose a proton to become the hydrogen phosphate ion with a 2- charge, and the hydrogen phosphate ion can also undergo equilibrium to lose a hydrogen ion plus the phosphate ion. Now, regardless of how many protons we have, each of these protons has their own equilibrium expression and their own Ka value. So as we start to look at these, we can think of a very similar situation to what we've been doing. This? No. Because sulfuric acid is a strong acid. It's a one-way ionization. This is a strong acid. This ion is the conjugate base of a strong acid. It does not act like a base. It has no interest in going back and getting that proton back. But the tricky part is it's also a weak acid. So it does its weak acid thing. So that's why we never use a sulfate ion or a hydrogen sulfate ion as something in a salt, because it does its own chemistry. So let's look at the example of carbonic acid. We've got carbonic acid in equilibrium with a hydrogen ion plus a hydrogen carbonate ion. And we can write the Ka expression for this. Ka1, because I'm losing the first proton, is equal to the concentration of the hydrogen ion times the hydrogen carbonate ion divided by the carbonic acid ion. Carbonic acid, it's not an ion. And we can get a chart of diprotic acids and look up our Ka1 is 4.5 times 10 to the negative 7th. So when we start thinking about this, would we say from our previous criteria that this K is small? Yeah, we would say that's small, so we could ignore X. Okay? Now let's look at the second ionization. The second ionization is the hydrogen carbonate ion is in equilibrium with the hydrogen ion plus the carbonate ion. So my Ka2 is equal to the hydrogen concentration times the carbonate concentration, that's a 2 minus, divided by the hydrogen carbonate ion concentration. And Ka2 is 4.7 times 10 to the negative 11th. So when we look at this K value, is that a small K? Now, more importantly, is Ka2 small compared to Ka1? It is. So what that tells us is that the amount of proton that comes from the second ionization is going to be really insignificant when we're comparing it to the first ionization, and that's going to be important in simplifying the math. So, how would you expect the three ionization constants for a triprotic acid to compare in magnitude? Which would be the biggest? The first. So Ka1 would be bigger than Ka2, would be bigger than Ka3. So now we say, well, how do we determine the pH of a solution that has simultaneous equilibria? Well, we have to set up simultaneous equilibria. And we introduce our generic diprotic weak acid. We used HA to represent a weak acid. We use H2A as our generic diprotic acid. It just saves time in the writing. So H2A gives us H plus HA minus, and HA minus gives us H plus A minus. Now, if you find this confusing because we used HA before, then change A to something else. I don't know. If it makes you feel better, call it H2C. And then, yes. Sorry, there must have been distortion in the projection. Taro, you had a question? That was it? Okay. Thank you. Now, look at the Ka values for the subsequent ionizations. Well, usually, Ka1 is often much bigger than Ka2. So that means that the amount of proton from the second ionization is much smaller than from the first ionization. So, in a lot of cases, we can ignore it. But when we can't ignore it, we solve simultaneous equilibria by setting up two ice charts, or one ice chart that turns into what I call an ICE chart, ICCE. You have two lines for change. But I think those are more confusing, so it's easier to just do it with two charts. In order to do that, the polyprotic acid does have to be the only source of loose hydrogen ion in the solution.